today we have Andrew Chen. He's in the CS field, and he's going to talk about fighting procrastination and some other things about the CS field. Okay, so about E4I, Educators for Impact is a nonprofit social impact organization. Our goal is to increase access to education and educational opportunities. We help people, students, adults, experts, novices learn more about a wide variety of topics. We host webinars, we have YouTube channels, we try to spread information through there, and also other social medias. And we are welcome on our team. And here's our role, www.educators for the number 4 impact.org. Today we have a collab with another of our partner teams, SVYEP. Ray, would you want to start screen sharing?
Yeah, all right. So hello, Evan. Thanks for giving us the opportunity to be here today. I guess before we start and listen to Andrew's presentation, Ray and I would just like to introduce our organization, which is in affiliation with E4I, the Silicon Valley Youth Entrepreneurship Program, or abbreviated as SVYEP.
SVYEP is a business club founded by high schoolers whose purpose is to also help high schoolers through their journey of business.
What is SVYEP? SVYEP is a program that helps, an entrepreneurial program that helps encourage growth in entrepreneurial and other skills. Helps break down the age barrier to enter business, so you could do it as a high schooler or even middle schooler. And our goals is to become the largest student-run business club worldwide and to create social change from innovation.
All right.
Okay.
Good. So this is our founding team.
So why should you apply? Well, there's many student summer internship programs available with A+ companies, in-person meetup events, and online meetings with industry professionals. And all in all, they result in opportunities to engage in social startups, paid job opportunities, and alongside building a sense of community. And all of this is free. All you have to do is to look at our website. Next slide, please.
So how do you apply? To apply, you could either scan this QR code or use this link to fill out the interest form. And once you fill out the interest form, we will contact you through Gmail or through the contact information you put inside the Google Forms. And after you apply, you could talk to your local officers about leadership rules, and you could also ask them for any questions.
More information can be found on our website, SVYEP.com, alongside our socials. We should check them out for more information. And thanks, E4I.
So yeah, I'll link all their socials beneath the event description, so you can click on that after. But yeah, thank you.
My name is Andrew. I am right now a senior in college, and as I'm speaking right now, there's actually only 10 more days till I graduate. It's quite an exciting time in my life, and I kind of want to reflect and share my experience a bit. So personally, after graduation, I will start work in formal verifications, where the primarily technology I'm going to be working with is functional programming, and that's going to start in September. During college, I've done a lot of research in machine learning and software engineering. Went to a couple of conferences, had actually just one publish, and I also did a few internships for software engineering during my college time. And as for work, and actually where I grew up in is the DMV area, in particular Northern Virginia. Today, I want to talk to you about 4 topics that I think you should know about, and high school me would have appreciated a lot if I knew earlier. The 2 last topics are a little bit more CS oriented, so I think I'm going to still go into depth for them, but I will definitely make sure I emphasize the first 2, the more general advices, a bit more. First, I want to talk about nature of procrastination. Then I want to talk about the academic must-dos, especially for college, during college. And then I want to talk about, first of all, functional programming, which is a a paradigm of programming that I'm actually going to be working with primarily during professionally. And then I want to talk to you about a really exciting new field in machine learning called mechanistic interpretability that I think you should study if you want to get into machine learning. And then last, we'll have a little bit of an Ask Me Anything session. The nature of procrastination. So sometimes procrastination can be a great tool. The way that some people function is that they are productively procrastinating. And sometimes they can generate better art because they just let their unconscious dissolve and break down the task at hand so much that when it comes time to crunch that deadline, they just produce the best result. But in general, the procrastinations that we usually face are, not doing our homework and not being on top of our assigned tasks. So how do you defeat these? And in general, how do you achieve the end goal of learning materials? Procrastination has always been a struggle in my life, and it's one of those things that you can't just solve once. Personally, in the past 8 months, because I've been working on my thesis, which I'm actually defending on next Monday, I've just been in this hyper-focused state. I'll be taking Metro, but on the Metro, I'll still be reading academic papers on my iPad and annotating. But in the last 2 weeks, after I submitted my thesis on April 19th, I just went into a full sort of brain rot state. I'm playing video games every day. For the past week, I played easily 30 hours of video games. And I feel like I have more aptitude for eating junk food. I'm not going to the gym anymore in the last 2 weeks. And my message in that is, you can't just solve it once. It's very easy to get sidetracked. But in general, when I do need to stay focused, and which I did for, I want to say, the majority of the past few months, is one simple thing, and that's you want to love the state of being focused. Think about that one time when you had just maniacal focus and nobody can break them. I always think back to one particular scenario in high school when I came back from school. My cousin was on the couch and she wanted to invite me to watch some Nat Geo, but I just finished like an easy task, like an easy busy work already, and I was just somehow in the zone. And I remember I had this such insane focus that I can hear the Nat Geo episode playing from her living room, but my mind was just focused on the textbook that I was reading on my computer. And sometimes I think about an image just exactly how much I love the state of waking up at 5 a.m. and putting in that 2 hours of work and then seeing the sunrise. You need to practice loving this state. And when you love the state of focus so much, you automatically identify when you are unfocused. So it might be quite a large leap from being, let's say in a rotting mode in your life to all of a sudden becoming this disciplined and focused person. So I want to say that maybe in the beginning, you can even just practice having focused distractions, right? When you're playing video games, when you are seeking entertainment, at least just focus on that particular thing at hand. Don't be playing 2 video games at the same time. I'm not sure what video games you can play at the same time, but don't do that. Don't be watching a YouTube video and then trying to do your homework at the same time. If you're trying to watch and have fun a YouTube video, then do that thing alone. This is just one simple rule that I find to be extremely effective for whenever I need to get on track. If you want a little bit more science to this craft, I highly suggest a blog that Oh, I think Evan actually made it into a bit.ly code. Thank you very much. So you can scan that QR code and read a blog about that. And then if you want to read any self-help books, the only recommendations I have is probably Atomic Habits and Deep Work. These two work I do use from time to time. And they give you a deeper structure about how you should approach, I suppose, a meaningful life. And of course, when you set up identities of what you want to be, then tackling the daily task of not being able to focus is a little bit easier. The next thing I want to talk about is the things you got to do in college, at least academically. I think first and foremost, you should challenge yourself to write a thesis. It is kind of weird, a weird advice because, and I personally debated about this for a bit because I had a chance between working part-time and doing more pure research rather than writing a thesis. But I believe that writing a thesis improves your ability to argue and present some complex things in a step-by-step manner. And that ability is just something that can be best learned through writing something that large, right? Writing something on the 50 to 100 page scale. And also, this is a perfect chance for you to just indulge in a topic that you really liked. In college, I really didn't like to the things that I ended up doing research for. There wasn't any undergraduate classes for them. I ended up doing research in adjacent research in mechanistic interpretability, machine learning, a little bit of software engineering tooling, and there were no exact classes for them, and no class will be at the depth of allowing you to do projects at that level. So thesis is your perfect opportunity in doing that. I would 100% recommend this. If you take anything away about this college advice section, you should definitely write a thesis. You should definitely start research ASAP. I didn't start research until towards the end of, I think, towards the beginning of junior year. And I could have just done a lot more. I ended up still having one publish, but frankly, it wasn't at like a top venue. So if I do want to get into a top grad program, going that route is still a little bit more challenging because I didn't start research earlier and have more of those opportunities. The third tip I want to give you, and I phrased it in this controversial manner so that you can maybe better remember it, is that there are stupid questions. Now, to me, the biggest indicator of a good software engineer is in how good they are at asking questions. I personally used to ask questions that didn't really consider the other person's time. I used to just have a question and ask it. And over time, I got the feedback. Like eventually, I think I realized I was being annoying. And that's when I started realizing that sometimes asking a good question is actually about considering, a big part of it is consideration for the other person's time. So now when I ask a question, I always detail the researches I've done to that point. I always put in my thought behind the question and why I am now stuck. Because I think asking questions is a more social is more social science and more social engineering than it is computer science. It is always pure. You're going to be when you're actually working as a software engineer, you might be going up against questions that are really complex and really only apply to your architecture and your infrastructure, such that you have to ask somebody on the team. In those cases, you still want to show that you did your research, you respect other people's time. you should definitely not be asking questions that you can find on the first page of Google or the first 3 items of Google, let's say. And nowadays that ChatGPTs are a thing, I would even go overboard to saying that if your answer can be addressed by ChatGPT, then do that first. So really, when it comes to having stupid questions, I guess there are no stupid questions. There are just questions that you haven't done enough research about. So respect others' time. Do the research, and those will be good questions. And I think good questions immediately give people good vibes about you. I personally have received compliments about my questions, which I think is a beautiful thing, after I learned how to ask good questions. The fourth thing I want to talk to you about is you always want to be choosing doing things that are hard more than things that are complex. Now, there is a big difference between what's hard and what's complex. Hard is something that is purely hard. Math in general is hard, right? Computer science, on the other hand, in my opinion, is more so complex. Theoretical computer science, yeah, very, very hard. But the software engineering that you do, learning different languages and learning different libraries, that to me is more so an issue about complexity. You want to be choosing the thing that is hard because that's what grows the unconscious capacity of your brain the most. Right? There'll always be another language, there'll always be another framework. You can always learn the knowledge that are more so complex. But what's hard just takes time, just takes a certain amount of sleeps to digest that knowledge. And to be really honest, looking back at the majors I chose, I should have majored in math. I ended up still taking a lot of math courses. I'm probably 1 course away actually from being a major. But I spent a lot of time in computer science dealing with things that are just complex. And those things change. My personal thesis actually had like maybe 2 shifts in the overall topic because developments in machine learning were just way too fast. And I wasn't answering fundamental and profound questions about machine learning, such that by the time I was coming up with solutions, some papers were already coming out with new stuff addressing exactly those things that I wanted to answer. And the last thing on the topic of academia and your college academics is you want to set up a learning framework as soon as possible. And so I actually want to show you some of the notes I took with the software Obsidian. So I will now share screen for that real quick. Can you guys see this?
Yeah.
Sounds good. So when it comes to taking math notes, the strategy that I've developed that helps me just digest everything is when it comes to a textbook, I always have 3 markdown files that I organize. I always have a file dedicated solely to definition, a file dedicated solely to theorems, and then my last, a folder including summaries for every single chapter in the book. This is just honestly how math is organized. If you understand every single definition and every single theorem, that is the core of the textbook, right? Of course, there's the problem-solving process, but these 2 are the core of any math. So in this particular case, I'm in the field of algebra, and this is really just the exact definitions that I took from the algebra book that I was assigned 2 semesters ago. And I organized all of the definitions in a single file because really you're not going to have that many definitions. And then the same thing for theorems as well. But then when it comes to summaries, of course, these are chapter by chapter. And these just, the reason I do summaries sometimes really is just to make sure that that stays in my brain long term. After I craft a summary, it's just a lot easier for me to revisit and regain this knowledge when I come back to it. Because really, if I want to read a definition of theorems right now, I'll be still a little bit lost. It's just a lot better to read these summaries. So these are a gradual process. I don't build these up in a single sitting. As I'm reading a textbook, I am directly, whenever I encounter a definition, I'm directly putting that here. Whenever I encounter a theorem, I'm directly putting that here. And these summaries are done after chapters. And I think this is honestly just the key that enabled me to get good at math. I remember in the first probably 2 years of college, I actually dreaded math. And I usually only got B's in these courses. But honestly, right after I started using Obsidian, which is this application that you're looking at, and just set up this good learning infrastructure, I just started rocking those classes. There's probably 2 more things that I want to mention. For mathematics in particular, I also have an examples folder. This is, so for certain definitions, certain definitions are generic concepts, and these are concepts that have many examples to satisfy them for. And so this file is dedicated to all of that. And then I have miscellaneous stuff here, exercises and notes. And then one more thing that I want to talk about that this app is really cool for is you can install some plugins. And there's actually a lot of plugins in Obsidian. And I use this thing called spaced repetition. So sometimes when you are, especially when you're dealing with complex knowledge, in my opinion, there are things that you want to just remember. So I was working on Haskell the other day, and let me see a note card that I took. I think it was something like variance. And you can, oh wait, not this one. You can write, you can design flashcards in this particular manner, separate the front side and the back side via a question mark. And then it's going to go into this little tab right here, review flashcards. And you can go through them. This is the front side of the card. You are going to think about what the answer is. If you can answer it, then maybe you say, hey, let me revisit this concept in 4 days. Now, as you get better and better at this, the algorithm is going to eventually maybe not even show a card anymore because you have eventually memorized it. So these are, yeah, this is the biggest thing I want to show you about setting up that studying framework. Just start using Obsidian. You make your notes more digitized. The only other big piece to how I study is probably my iPad. I download the PDF forms of papers and textbooks onto iPad, and I directly take notes and annotate using an app like Notability. And eventually, when I'm done taking notes for a textbook or a paper, I can import them into Obsidian and maybe do a little bit more work and synthesis work right here. So yeah, I'm gonna go back to the presentation now. Does anybody want me to show anything else maybe? Or any questions thus far?
So I'll probably link Obsidian in the meeting description as well, but can you quickly show how you install plugins for the application?
So you come here to settings, and then you come to community plugins, and then you just click browse, and then you can search for plugins. So there's honestly a lot of plugins. There is probably anything that you think is learning related and can be packaged as a plugin. There's probably a plugin for that. I cannot think of examples on the top of my head, but spaced repetition in this case is, if you just look it up, you can just install it from here. This is cool. Spaced repetition algorithm.
Okay.
Yep. Anybody else? Okay, I think I'll move on. And by the way, does anybody here actually plan to major in computer science? Just out of curiosity.
No.
I mean, I want to do AI, but kind of related.
Yeah, I mean, 100%. I mean, so maybe you'll be a little bit more interested in the mechanistic interpretability stuff that I want to talk about. Yeah, so I mean, I know this is going to be recorded, so then in that case, I definitely still will go into detail about them. But yeah, the upcoming slides are a little bit more CS oriented. All right. Does this look good? Is it
Yeah.
back to the
Yeah.
screen? Okay.
It's good.
All right. So now that we're done with the general advices, let's move on to the more CS specific ones. In particular, I want to introduce two fields that may be unfamiliar to you right now. The first one is functional programming. This is a different paradigm of programming. Most people probably know Python, probably heard of Java, but you might have not heard of things like languages like Haskell, F#, Clojure before. It is quite a different way of programming versus object-oriented programming. And in the words of Dijkstra, he said that facing students with a novelty of functional programming immediately drives home the message that there is more to programming than they thought. Functional programming is, as its name suggests, very modular and organized around functions. Functions become first-class values in the language. So that's actually a little feature that's implemented in Python, and actually even Java nowadays if you use some extension. But just having the fact that functions can be values enable a whole different way of thinking about programming. And Haskell is in particular a specific functional programming language that implements a whole bunch of different ideas. Few things include algebraic data types, type classes, and those things enable a deep connection to category theory, which is probably the most complicated math field there is. Category theory is a math field that's all about lifting things into these concepts, kind of similar to abstract algebra, which I showed the notes of earlier. You are trying to see if certain structures you're studying satisfy some certain prerequisites for being a certain kind of thing, such as a monad. And once you are, let's say, a monad, then all of a sudden you satisfy all of these other theorems because they've just been proven for them. So Dijkstra here has a quote, and he honestly is kind of a hater of object-oriented programming. He thinks it is an exceptionally bad idea, which could have only originated in California. And Alan Kay in response says, I don't know how many of you have met Dijkstra, but you probably know that arrogance in computer science is measured in nano Dijkstras. Alan Kay, of course, is one of the pioneers of object-oriented programming, who invented Smalltalk. So originally what actually captivated me about functional programming is actually Dijkstra's opinions on these things. Dijkstra is a legend of programming. I'm assuming that he must have received a Turing Award at some point. But he's the man. He's the man. But of course, I'm aware that in the real world, people will be programming with object-oriented programming languages, programming with Python. Honestly, nowadays, I think Python is pretty elegant. It borrows some of the most important ideas of functional programming, such that in many cases, that's all you need. If you want to learn more about functional programming, if you are enticed about sort of this alluring description that I gave you, then check out this FP Learning, Functional Programming Learning Journal that actually I took. This is a link to my blog when I was learning Haskell. It has about maybe a year worth of content. Just me logging day to day what I learned, what are some of the jargons and concepts you encounter. And then if you are a programmer, and maybe let's say you haven't done any functional programming before, I have 2 challenges for you. So actually, besides Dijkstra's obsession with functional programming, I was also brought to functional programming because the principal engineer at the first company I interned for sent me the book Mostly Adequate FP Guide. And actually in that book, you're doing functional programming in JavaScript. And it was very enlightening. And I think if you haven't thought in that way before, or if you know how to do JavaScript, you should just check it out. You should just do it for fun. The second challenge is, this is a lot more challenging. If you have done challenge 1, maybe you'll be interested in challenge 2. The second field I want to talk about is mechanistic interpretability. Machine learning is growing at an alarmingly fast speed. I mean, I'm sure that some of you guys have used ChatGPT before, but I feel like we truly are on this stage that maybe soon of programmer jobs can be taken over. AIs have already started taking over some jobs because some code are just as easy as that. But today you're seeing agent-based models just completely writing code from scratch. And in fact, there was a study recently. Some folks created an evaluation benchmark called SWE Bench, Software Engineering Bench, where they took real GitHub pull requests. They took real GitHub issues and just gave it to agent-based models to solve. And these are real issues, could be of any complexity. They gave the models access to a code editor and a debugger and also the browser. And the model was able to solve like 12% of just random issues on GitHub. I think that's hugely impressive. But I also heard that maybe the company behind this is faking some of the data. So we'll see. But overall, these things are moving really quickly, right? If not in the text domain, then you've seen their progress with things like Sora AI, which can generate, honestly, videos to me that just seem incredible. With capabilities growing so fast, interpretability has lagged behind. We might have heard the analogy that machine learning models are really black boxes. You train it on pairs of inputs and outputs. And then when you feed in new inputs that are similar in that original input distribution was trained on, it will give you the corresponding correct outputs. It is a black box, but the idea is about interpretability is that these weights, these little internal details going on inside of the model can be reverse engineered into something that is human interpretable. So I want to present maybe 2 key results that mechanistic interpretability has offered. The first result is a lot more important, but it does require maybe some prerequisite on knowing how large language models behave. And by the way, large language models are just what text machine learning models are called nowadays. Once you get to the 10 billion parameter stage, you start to become, you're called large. So induction heads. When you interact with ChatGPT, it is able to understand your prompts. Of course, it is able to follow your instruction. But perhaps what is even more impressive is that if you talk about some new thing in the prompt, the model can understand that. So that seems like something very easy to do. But the core of machine learning models, we must realize, are just things that are trying to model language. It is trained on the next token prediction objective, such that you are training models on let's say sentences for now, and you're training them that when they see things like a quick fox jumped over a brown fence, that when it sees a quick fox, it knows to predict brown. When it sees the quick, it knows to predict fox. And it doesn't really make sense why, let's say, if you mention Harry Potter for the first time in your input prompt, that when the model is predicting, that the model just all of a sudden has knowledge about or the ability to predict Harry Potter. Induction heads turns out to be the core principle behind how machine learning models achieve this behavior. This behavior, by the way, academically is called in-context learning. So I have a diagram for induction heads on the right. I think I'm just now realizing how complex this is to explain from scratch. But I'll still try to do this, I guess, a little bit high level. First of all, transformers, which is the architecture behind machine learning models, are hugely linear structures. And they're linear in that they can be approximated with a linear function. Linear function has mathematical meaning. It means that when you add something and then apply the function to it, it's the same as applying the function and adding the results together. And these are linear except for the feed-forward layers. In the feed-forward layers, there's something called activation functions going on, and those get to be nonlinear. And then it is actually a proven theorem that if you have these activation functions and if you have any other linearities, then when you combine them, you are actually able to learn anything. That's something that's called the universal approximation theorem. So transformers are hugely linear structures. Oh, and by the way, I'm just now seeing questions in the Q&A section. Sorry about that. I'll answer them right after I'm done with this slide, I suppose. Transformers are hugely linear structures, and they have these little modules going on that are trying to provide biases for the model to potentially learn useful things if it's trained on a next token objective. So these biases that are implemented at architecture time include things like self-attention and the add and norm layer, which in literature is called residual stream, or the residual layer, and then layer norm. What the attention layer is doing is it's allowing tokens to look backwards in the tokens that were provided in the context, such that because they should be allowed to use that information when they're predicting the next token. The residual add thing, on the other hand, you might only be able to understand this if you sort of understand activations in models, but the idea is as you progress in the number of layers as you progress in the layers in the model, usually these features that are learned at every single layer become more and more abstract. If you inspect, by the way, an image model, then, and if you put in the right weights, you can actually see the features that models have learned. And you can often see that in the early layers of image models, they are extracting things about extracting edges, extracting maybe the color theme of the image. But then in the later layers, you start to see actually complex features like dog heads and trains being able to be detected in these layers. The same thing works with a textual model. Features become more and more complex as you go down in the layers. And the idea of a residual add layer is that instead of learning these layers from scratch, you want to use the previous layer, because it is just a bet that these layers will compose in a complex way. So it's better to start from something already existing from the last layer than it is from a completely newly initialized one. So with these all together, you have a transformer. And induction head is actually a behavior that can be observed in a transformer with just attention. It doesn't need any feed-forward layers that actually learn the nonlinear complexities at all. And this right here, this K composition graph, quite just directly describes the algorithm. And honestly, I think it's a bit hard for me to explain the exact details of this thing. But I think the best thing now that I introduced the background is just to refer you to the links for this diagram and corresponding exercises, which can be found in the ARENA program that I'm hovering over right now. The ARENA program is pretty good. It covers a lot of other topics in mechanistic interpretability. So this topic right here, induction heads and finding induction heads, is in the general theme of reverse engineering a behavior, reverse engineering some algorithm, right? You see a model behavior and you want to see if are there fundamental weights and compositions going on that allows for that to happen. But there are definitely other fields in mechanistic interpretability. The reverse engineering the features that image networks learned that I previously mentioned is a topic of mechanistic interpretability. Some other subtopics involve can we maybe something called steering vectors? Can we inject arbitrary vectors at inference time to deterministically change the outputs? So the last important thing that I want to mention is that sometimes you just find that learning certain subtopics in a field allows you to learn all other topics in the field easier. I want to go and say that in general, going back to the pure and complex thing earlier, that the more pure thing you learn, the easier it is for you to learn complex things. I find in my personal experience, and all of the personal interactions I've had with people that transitioned from math undergrad to computer science PhD, they just simply had an easier time. Things just clicked faster in them. So that's a very large generalization of this pattern, but in the case of machine learning, I think if you can figure out mechanistic interpretability and learn these materials, it will just make you a better machine learning person, a machine learning researcher. And I think the main reason for that is in mechanistic interpretability, you need to know exactly what is going on inside of your networks. And quite frankly, if you're just a working engineer, if you are somebody who uses the model or just does some pretty crude fine tuning with the model, then maybe you just don't need to know these details. So it's really attention to detail thing. And personally, in high school, I took the machine learning course by Andrew Ng, and that just simply wasn't enough for understanding the new architectures of today. So if you're trying to get into machine learning, I think a good way to start really is from the ARENA program. Again, sometimes if you learn certain subtopics, it will just allow you to learn the general field better. And in this case, I think that that is a relationship between mechanistic interpretability and the overall field of machine learning. So with that, Oh, I am actually just done. So with that, ask me anything. Let's go into this stage. Oh, and actually, you guys don't have to ask me anything right now because there are some things I need to answer in the Q&A. Ethan, let me keep on sharing this so that the presentation looks better. Ethan asks, how big of a role did mathematics play in your CS major? I think mathematics allowed me to embrace hard things. And I honestly think that when I was just like a computer science enjoyer, I was just kind of afraid of whenever I saw like hard computer science stuff. So functional programming in that case is something hard. Theoretical computer science, anything that dealt with lambda calculus or maybe Turing machines, finite automata, I just sort of strayed away. But after I took mathematics seriously, and again, I think the way you take mathematics seriously is you stop studying them as just courses. You actually organize your knowledge about mathematics in a manner that, for example, I did in Obsidian. And you and yeah, I mean, I'm trying to think if I can say anything about mathematics. I had one more thing to say about mathematics that I planned earlier. Yeah, one more thing about mathematics. When you're learning mathematics, the most important advice I can give you is to just read the textbook and read the textbook line to line. If you don't understand one line, you cannot proceed to the next line. And I think learning materials in this way, in this whole and complete manner, allowed me to just become better at computer science as well. Because whenever I want to understand a concept, I'm more so encouraged to understand everything as a whole, and I make sure I do not miss out on any prerequisites. And you really see this being a big factor between good and bad researchers. Good researchers understand the reason that they're doing things, and you can only understand why you're doing things when you understand absolutely everything about the prerequisites, everything profound and fundamental about your field. So again, that's also one of the reasons why I took upon myself to learn mechanistic interpretability. I wanted to machine learning research, and that just allowed me to fill in all of the gaps and made me a lot more confident in machine learning.
Okay. If there's not any more questions in the QA, we have some of our own questions that we would like to ask.
Yep, there's no more in the QA.
Okay. So
sorry, give me a second.
what? Okay.
Sorry, Ethan just gave me a question. Should I answer this one first, or do you want to?
Yeah, you can go ahead.
If you're interested in AI, is it worth trying to get into it in high school, or do you recommend learning the math behind it and save the actual AI/ML stuff for college? Excellent question. Excellent question. Give me 1 second to think about this. So, first of all, in the particular case of math for AI, let's talk about what are the math for AI. There's linear algebra, which is fundamental to machine learning because everything is matrices. But there's also the very interesting sort of this high level view of machine learning you can do with mathematics that I don't think is being exactly mentioned here. but I do want to mention it briefly because there's levels to math in ML. And I honestly think that in high school, some of the very advanced math in ML might just be inaccessible to you just because of you don't have enough time. So if you're interested, you can check out the fields geometric deep learning and topological analysis. And while you're on it, maybe check out singularity learning theory. These are all fields that use mathematics to prove fundamental things about machine learning. And the keyword here is prove. In general, the basic working pieces with machine learning, like linear algebra, are just utilities. Like linear algebra is just a nice way to describe machine learning, but it's not fundamental to it. What's fundamental to it is how the features, for example, are represented in machine learning models. Why, let's say, why can we expect that non-linearity when combined with a little bit more biases can build you something that can learn anything universally? Why is it that something that seems to have a lot of linear structure, that is most models, can learn something so complicated? And there are some hypotheses about manifolds in that. And while you're on it, you can check out something called topological data analysis, which I'm not sure if I mentioned just now, that studies the shape of the representations that is learned by your models using topology. So, therefore, it's a little bit hard for me to answer this question because I'm not sure exactly how much math you should learn. But in general, my advice would be to try to, if you have the motivation for it, to learn the hard thing before you learn the complex thing. In this case, I would think that machine learning, large language models, how they operate, that's a little bit more complex, and the actual math behind it, so the fundamental stuff like linear algebra, are definitely more pure, and it is better to get into that as early as you can. A lot of stuff in machine learning that is popular are actually very experimental. They don't really have a mathematical intuition behind them, but you'll find that the most impressive research in machine learning all come from like people that are really cracked at math. Actually, just recently, I'm talking 3 days ago, some folks released something called the KAN, which stands for something like Kolmogorov-Arnold something network maybe, that gives us a completely new outlook on the fundamental building block of transformers, which are the multi-layer perceptrons. These have always just been learned with fixed activation functions, but what KAN proposes is, what if these activation functions, these functions that are supposed to help us learn something, are actually not fixed, and these are actually learnable. Supposedly, this is not a new idea, but the authors somehow made it work. And this has been, some people call it an end to deep learning, because this is like a new mathematical structure that can just allow you to learn things in a pure way. And this kind of research can only come when you're really, really adept and good at mathematics. So hopefully that's like a comprehensive view of towards your question. Yeah, if you have any more, let me know. Yeah, I think now maybe we can go on to your questions.
Yeah, okay. So what advice would you give to someone starting out in the computer science field in general?
What advice? One advice I love to give is read the purest information there is. Read the best sources for information there is out there. When you approach a concept, you have multiple sources to utilize in learning it. You can choose a medium.com blog post. You can choose Wikipedia. You can choose Reddit comments. You can choose also research papers and textbooks. My recommendation is always choose textbooks and research papers before blogs. I think people put much more time and thought behind how to organize ideas in textbooks and research papers. And it's also one of the reasons I would recommend writing a thesis, is to allow you to go through the process of getting good at really expressing an idea. That's number one advice I'll give. Always access the best source there is out there. Maybe a second thing, maybe I can talk about imposter syndrome real quick. You might look around your peers, and let's say you go into computer science and in college, and you didn't do any of it in high school. Then by the time you're starting that in college, you're going to be behind everybody else 100%, because people that tend to do computer science are just interested in it, rather early on. But what's the difference between you and them is not like a skill issue. It's not a learning issue. It's just a time issue. Putting more time and you will reap the seeds that you sow. And if you find yourself in a situation where, let's say, you and another person started learning at the same time, but they accomplished more than you, then also don't be sad. Like, that person probably spent more time in analyzing how they can learn best. It's always a time issue. Put in more time, and I think you'll definitely see the reward. So that's my second advice.
And that's more general.
That's definitely, yeah, that's 100% more general. I mean, that's for everything, right?
So what advice would you give to your younger self with the knowledge you know now?
If we're talking computer science, then I think honestly the advices that I'll give to my younger self are very much so covered between the Q&As that we just had and also the presentation that I gave. I mean, honestly, when I curated this PowerPoint, I was thinking, like, what would I have told my younger self? But I guess on life, on the outlook of life, I would just tell my younger self to not be so stressed out of trying to become somebody or trying to find meaning and purpose in life. I mean, I still don't know really what the hell I want to do in 5 to 10 years. Like, I know I'm going to be working at this job, but afterwards, like, maybe I can be doing other stuff, don't be so limited about what you can do. Everybody has multiple intelligences. Academic stuff is just one intelligence, but there's so much more than that. How you're able to interact with people, your body intelligences, your experience with nature, those all matter, and those are all skill points that you can grow. So yeah, maybe I tell my younger self, not be so anxious. You're always learning. You're always going to survive. I remember this one particularly funny story, and this I've been thinking about recently much more. And in high school, I had this one teacher. His name is Mr. Sargent. He taught me AP Econ. I think this was junior year. And he seemed very smart. And he seemed like he got everything figured out. And I just wanted to say smart things to him, I guess, to show off that I'm smart too. I'm on his level. I can be on his level too. So I remember one time after class, I swear I must have read some anarchist writings the other day. And I just went up to him and I was like, Mr. Sargent, I think my political views, I think about my political views, I'm a libertarian. And he just laughed and he's like, hey, that could be you today, but we're all figuring out, and I'm still figuring out. And I think the statement of he is still trying to figure things out just brings a lot of calm to me. And that's the exact statement that I'll bring to my younger self.
That's good advice. Yeah.
Yeah.
But yeah, that's everything from me. So if that's it, I guess, yeah, we can move on to the socials slide.
Sounds good. You guys can still see the slides, right?
Yeah.
I think it's still showing. Okay. Yeah. There's my YouTube, my blog. So maybe there's a way for you to share the slides because these are, hyperlinks.
Yeah, I'll be linking everything talked
Yeah.
about during the
Sounds good. Yeah, I'm trying to resurrect both of these right here, my YouTube and my blog. My blog is sort of like my blog is more documentary. I write about the things that I learned about. So maybe this will be interest to the CS folks that are coming up. And on my YouTube, I used to post a lot of tech content, and I'm trying to resurrect it, post some meaningful content now. So yeah, that's it. That's it from me. Thank you guys.
Okay. Yeah, that's wonderful. Okay, thank you.
Cool. Anything else, guys?
If there's no more questions, I guess we can end it here. But yeah.
Awesome.
Okay.
All right. Take care.
Yeah. Okay. Thank you.
Thank you.
Yep. Bye-bye.